You've probably never actually seen it, but the technology we're diving into today has literally shaped almost everything around you. I mean, it's a way of seeing the invisible, all those hidden stresses and strains that decide whether our greatest creations stand strong or crumble into dust.
I mean, just think about the kind of challenges engineers are up against. How can they know, for sure, that a brand new skyscraper can actually survive the incredible violence of an earthquake, right? You can't just build a prototype and see what happens. You have to know before a single beam is ever put in place. Or hey, what about the car you drive? We all want better fuel economy, and that means making cars lighter. But how do you take weight out of the frame without making it weaker? Getting that balance exactly right, well, the safety of you and your family literally depends on it. And then you bring it down to the human scale. A hip implant has to deal with unbelievable forces, day in and day out for decades. A failure here isn't just some product recall, you know? It's a huge deal for a person's life, for their health. So, how in the world do engineers tackle these massive, sometimes life-or-death problems? Well, it turns out the answer to all of these questions comes down to one really powerful method. It's a way of taking an impossibly complex problem and just breaking it down into simple, manageable pieces. It's called finite element analysis, or FEA for short. And the core idea, honestly, is brilliantly simple. I want you to think about a high-res digital photo. It looks really complex, right? But if you zoom all the way in, it's just a grid of millions of simple little colored pixels. FEA does basically the same thing, but for physics. It breaks a complex object down into a huge number of simple little elements. So how does it actually work? Well, it's this really logical four-step journey. First, you start with a digital 3D model of whatever you're testing. Then, and this is the cool part, a computer divides that model into a mesh of millions of simple little shapes, like tiny pyramids or cubes. From there, you apply the laws of physics to every single one of those tiny elements. How does it stretch? How does it bend? How does it heat up? And finally, the computer puts it all back together, assembling the results from millions of these simple calculations to show you exactly how the entire object behaves. You see the big picture by understanding all the little pieces. Okay. So that's the theory, but where this gets really incredible is what it lets us do in the real world. I mean, it has totally changed how we design and build, well, pretty much everything.
And believe me, this is a massive shift. Back in the day, testing meant you had to build a physical prototype. It was slow, it was super expensive, and often you had to literally destroy the thing just to see where it would break. But now, with FEA, engineers can run endless virtual tests. They can simulate 1,000 car crashes, tweak the design with a click of a button, and test it all over again, all before a single piece of metal is even cut. It's a game changer.
I mean, just look at the world around you. FEA is kind of like the silent guardian of our cities. It's used to analyze the stress on every single girder in a huge steel bridge, to model how a skyscraper will sway in an earthquake, and even to simulate how a tunnel will interact with the soil around it. And it's not just big structures. It's inside the machines that power our daily lives. FEA helps optimize everything from a tiny little connecting rod in your fridge all the way up to those massive gas turbine disks spinning at thousands of RPMs. It's what helps engineers design those lighter, stronger car frames and make sure that spacecraft can handle the absolute vacuum of space. And this is where it gets profoundly personal. FEA lets engineers model the exact stresses on a dental implant, or simulate how a stent is going to expand inside an artery, and even design prosthetic limbs that are perfectly optimized for a patient's body and their lifestyle. It's bringing engineering precision right into the heart of modern healthcare. So this really brings us to the crucial takeaway here. FEA is the ultimate virtual testing ground. It gives engineers this incredible power to explore, to really understand why things fail, and to perfect their designs in the digital world, long before they have to commit to expensive and time-consuming physical production. Okay, but here's the thing. This technology isn't just standing still. The very same digital revolution that gave us FEA is now pushing it into a whole new era, making our ability to design and predict smarter, faster, and stronger than ever before. So, as we're inventing all these incredible new materials, FEA is evolving right alongside them to predict how they'll act. It can model things like hyper-elastic materials for earthquake-proof buildings, or, get this, piezoelectric materials that actually generate electricity when you squeeze them. It's even being used to design so-called 4D printed structures. We're talking materials that can literally change their shape over time. And of course, the next giant leap is plugging FEA into artificial intelligence. AI is taking FEA from being a pretty slow, calculation-heavy tool and turning it into a near real-time predictive engine. This is huge. And this unlocks incredible technologies like digital twins. Now, what's that? Imagine having a perfect virtual copy of a real-world bridge, running simulations 24/7, predicting maintenance needs, or even failures long before they could ever happen in reality.
And maybe the ultimate frontier, the holy grail, is something called multiphysics. This is where simulations get really wild. They don't just look at one force, like stress, but they model the complex dance of everything at once. The structural loads, the heat, the electricity, the fluid flow, all of it. So imagine simulating not just the wind hitting a turbine blade, but how that force makes the blade bend, which then changes the airflow around it, all happening at the exact same time.
So, all of this brings us to one final thought. Finite element analysis has already let us build a world that, honestly, would have seemed like science fiction just a few generations ago. So as this tool for seeing the invisible becomes exponentially more powerful, more predictive, and more intelligent, the question is, what will we be able to imagine? And what will we be able to build next?